Hello everyone, this is Nash. Today I would like to introduce you the concept of Molar specific heat of a gas at constant volume and at constant pressure. But before I talk about the concept of Molar specific heat, I would like to help you to remind similar idea like the specific heat, S. Yes, that's why we choose the S as the symbol. H equals mA delta T. You must be familiar with this formula when you were a junior high school student. So look carefully. What is the physics meaning behind the S, behind the specific heat? It's not hard to discover that the S is equal to the H divided by your mass and times the change in temperature. So you need to train yourself to express the physics concept behind the formula and behind the definition. Okay, maybe you can practice with me. What is the definition for a specific heat of a substance? That is the energy it required to raise the temperature by 1 degree Celsius or 1 Kelvin for a unit mass, like 1 gram or 1 kilogram. That is the definition for the specific heat. Alright, after reviewing the definition of specific heat, I think you are ready to learn new things like the molar specific heat of a gas at constant volume. Usually we use the symbol C sub V as the topic we would like to talk about today. And the CV, let's talk about the definition first. That is the energy required to raise the temperature of 1 degree Celsius or 1 Kelvin for a unit number of gas, for 1 mole of gas. So this is the definition for molar specific heat at constant volume. The energy required to raise 1 mole of gas by 1 degree Celsius or 1 Kelvin. That is the definition. If the volume is now a constant, then all the energy you are now absorbing will be all transferred as the kinetic energy. That means all those molecules are now flying even faster. They are increasing the kinetic energy, and that means they are increasing the internal energy. So what is internal energy? Internal energy, U, is 3/2 PV or 3/2 nRT. 3/2 nRT. Now, the constant, the volume is a constant. All the energy you are now absorbing will be transferred to the kinetic energy, to the internal energy. And that means the energy you are now absorbing is equal to the change in internal energy. And the internal energy is 3/2 nRT. The N and R, they are all constants. So if you want to express the idea like change in internal energy, it should be written down as 3/2 nR and times the change in temperature. So let's now cancel the same item like the N, the moles, and the change in temperature and what we are left with is the 3/2 nR. That is the molar specific heat of a gas at constant volume. And what is R? R is 8.314 joule per mole and times K. I think you are familiar with this number. Alright, this is the concept of molar specific heat because the container cannot be expanded. The whole volume is a constant, so all the energy you absorbed will be transferred to the change in kinetic energy. And the kinetic energy for an ideal gas is the internal energy, right? So the heat you absorbed will all be transferred, will all be related to the change in internal energy. So that's how we get the C sub V is 3/2 R. So next time when you want to express the internal energy, the 3/2 nRT is not the only one. Is no longer the only choice. It can also be written down as NCV delta T. If you are a freshman in college, you might be even more familiar with this form, the NCV delta T, because CV is the energy required to raise the temperature by 1 degree Celsius for 1 mole of a gas. So NCV delta T is definitely the internal energy of a gas. All right, now I think you're ready. Maybe we can talk about something else, like the molar specific heat, still the molar specific heat of a gas, but at constant pressure. At constant pressure, P. The P should be a constant. Try to imagine you are now injecting energy inside a container. You're now injecting energy inside a container. Let's say this is a piston. More energy is now being injected inside a container. So the molecules now inside will fly even faster. If you're flying even faster, how is it possible I can keep the pressure constant? Because the force and the pressure is due to the collision, between the collision of the container and all the gases. And now they are flying even faster. They are punching the container even harder. So the pressure should be definitely be enlarged. So if you want to keep the pressure a constant and you are simultaneously injecting more energy inside, the volume is no longer constant. It should be expanding. It should be expanding, right? If you're now expanding, that means you are doing work to the outer system. You're doing work to the outer system. And what is work? Work is the force times the displacement. But in thermodynamics, I would like to write it down as the pressure and times the change in volume. Why? Because what is the pressure? The pressure means the force per unit area. The force per unit area. Now all those molecules are now flying even faster, and the collision between the container and the molecules, that means the force is now increasing. The force is now increasing. So that's why the container will be expanding. And there will be a F, and there will be an S. There will be a force, there will be an S. But the force divided by the area means the pressure, right? So let's keep the F right here, and the delta V is the change in volume. And the change in volume divided by the area, and that will be the displacement. So Fs and then P times the change in volume means the same idea. They are all work. They are all work. All right, let's now go back to the definition of molar specific heat at constant pressure. So let's practice one more time. Let's practice how to express the idea and the definition behind the CP. That means the energy required to raise the temperature of 1 mole of gas by 1 degree Celsius, by 1 Kelvin at constant pressure. At constant pressure. So since you realize that it's impossible for the whole system to stay in constant volume, So in all the energy you absorbed right now, it will not just useful to increase the change in internal energy, but also it is required to be done to the outer system. This is no longer the only item that you need to handle. You also need to handle the work that needs to be done to the outer system, and that is the P times delta V. P times delta V. The change in kinetic energy. Now we know the change in kinetic energy. The change in kinetic energy can be now written down as NCV delta T. NCV delta T. And what is the work? The work is the P times delta V. But P is a constant. Do you remember that PV equals nRT? So if P is a constant and nR are constants, so P times delta V is definitely nR and times the change in temperature. So I can express the work that needs to be done to the outer system as P times delta V, and also equal to nR times delta T. I think we are ready. We're so close. Let's cancel the same item like the n delta T, n delta T, n delta T, n delta T. All we are left with is the CV and an R. It's CV and an R. So the molar specific heat of a gas at constant pressure is equal to the molar specific heat of a gas at constant pressure and plus one more thing, that is the R. This is like the energy required to for 1 mole of gas to expand, and you need to raise this kind of gases by 1 degree. You should not only handle the change in internal energy, but also need to handle the work that needs to be done to the outer system. So that's why the Cp is larger than Cv. And Cv is 3/2 R, is 3/2 R plus 1 more R plus 1 more R. This should be 5/2 R. 5/2 R. But it should be noticed, all of this I only introduced you the concept of molar specific heat at constant volume and at constant pressure, but they are only suitable for monatomic gas. For monatomic gas. Monatomic gas in my mother tongue, 单原子分子. If you want to know the size, the CV and CV and CP for like diatomic gas, maybe I should introduce you the concept of degrees of freedom. Degrees of freedom. I think I'll talk it later in the future. But right now, maybe you can first memorize the size for the molar specific heat at constant volume and at constant pressure is 3/2 R and 5/2 R. Okay, for diatomic molecules, maybe I'll talk it later in the future. Thanks for watching, and this is Nash.